Okay, so let's start the next session. And in this session, I'm just going to give you a set of results that we have from physical mathematics. Some are, well, let's go and see what they are. This is, first of all, an overview of, this is an old picture that I still have. I don't quite know whether it needs to be retouched or not, but the general theory is essentially still in my head is made of 3 layers. One is the one that captures the notion of experimental verifiability, the fact that we have tests. And this is the part that is basically very solidly done. Then there is another part that should define essentially what is the information content of the statements, because this is what you can basically show that geometrical size and probability and information content, they are basically all things that you can go from one to the other. And so there might be a layer here that can be constructed in a way that is general, and it should also be the layer that defines the units and physical dimensions and all of that, because all those things are not like knowing that there are statements that are verifiable is not enough to tell you what units are. And so there could be a layer in between here that it's sort of above experimental verification. It tells you something more, but it's still not defining states, processes, and stuff like that. I always need to remember to do this. There we go. Otherwise, the cursor disappears, and it's very nice. And so this part is basically the part that we're going to take some parts from here. And this part is not very well developed at all. This part is actually more well developed. So I'm going to give you some results from there. So as we saw in the previous part, we have this notion of experimental verifiability that leads to topologies in sigma algebra. And what we're going to look here is that we can use this to define quantity from references. So again, we need to construct everything. So we need also to construct the real numbers and have physically meaningful assumptions that are modeling something that gets us to the real numbers. And the idea is when you create a reference scale, you have some references that define a before and an after, and then you basically find some conditions on those references such that that scale, the reference system, is going to define a real number. And then we're going to talk about instead the new work that we're doing on ensemble spaces. Some parts are some results are done. At least they prove and work well. Some other parts are instead to be cleaned up. And so I'm going to talk about this partly today because there are some results, and also partly tomorrow because there are open questions there, and I'm looking for people more on the math side to help me on those things to create essentially the structure that we need. So let's go and look at the reals. And this is like, to me, is probably the hardest bit of thing that I had to prove because yeah, it's you have to start with just this idea that you have these true and false, and you have these statements, and somehow you have to recover that there is an order and that you have the real. So in physics, we use real numbers to model physical quantities, and we actually need them. Like there are some people in the foundations of math that hate the reals, hate the axiom of choice, and all of those, and so they they try to really work without the reals, and there are substitutes for the reals to do some things, but as I said, we are not assuming that the real numbers are going to exist in some, physical, ontological sense. They're just in the model. And as a modeling tool, they're very useful because without the real, you don't get exponentials, you don't get Gaussian, you don't get like trigonometry in the trigonometric functions, and you use those all the time. So yes, it's going to be an infinite precision. Infinite precision is an idealization. We just need to understand what is the realm of applicability of that idealization such that we don't pretend that we go outside of the space. Right? That's basically what we want. Mathematically, there are many different ways to construct the reals. So it seems that it's like a mathematical sport to create your own ways to recover the reals, and there are lots. A lot of them are based on algebraic properties. So you see the reals as a field, as something where you can do addition, subtraction, multiplication, division with some properties. So those are the axioms, and then you recover the reals. You can see it as a Cauchy sequence of rationals. So you first, this is in set theory, for example, that's how you define the reals. You define the natural numbers, then the integers, and then the rationals, and then the reals as either Cauchy sequence or Dedekind cut of rationals. And if you have never seen those constructions, well, I'm not going to be able to talk about it right now in details, but that's sort of how you do it. And the issue is, how do we define them? Like, what is the proper way for us to do it? What is it that we should be modeling? And the most fundamental structure that we want to have in the real is, again, the topology, because that means where you're going to be able to say, the mass is between this range and so on. So as a first thing, we want the topology, also because when you go and study manifolds, for example, everything is defined in terms of a topology, and all the transformation that you might have are not going to be linear transformation. And so they're going to destroy essentially the field, the algebraic structure, because the sum of 2 points in one system is not the sum of 2 points in the other coordinate. So really the field structure is not the correct one. So what is the correct one? Well, if you look at topology and the topology of the real, you essentially use the order topology. The order topology is basically defines that all the set of something is greater than A or something is less than B, right? All these sets are open sets. And all the other open sets are generated by these by a countable, arbitrary disjunction and finite conjunction. And so this means that the object is after A and the object is after B are verifiable statements. And we don't know about the size. We just have references, and we're going to say, oh, it's beyond this reference and before this reference. And this really intuitive makes sense. Like if you get a ruler, we see all these notches. If we have a time, we have the clicks of the clocks, right? So this is essentially how we define quantities in physics. So it's very natural to say something is before, something after our references. So that's what we want to model. And so now the question is, can we can we characterize the reals only as a type of order? And it turns out that you can, and that's what Cantor did as a characterization of the reals. And it's very beautiful because there are not very many requirements. So unfortunately, I can't introduce order theory perfectly, but there are these essentially two facts that Cantor proved. First, that every countable, dense, linearly ordered set with no ends is automorphic to the rationals. So a linearly ordered set is one where you have elements that are always one after each other. So there are ordered sets that are not linearly ordered. For example, you could imagine to take a plane and define a direction, and so you can say that a point after this direction is going to be before a point that it was before along that direction. But then you're going to have 2 points such that none of them is before the other, right? Even in special relativity, you have light cones. Light cones define a causal order, but then you have 2 points that neither of them is in the light cone of the other, and therefore they're not ordered. There's no causal order between them. So not all sets are linearly ordered, but the reals are linearly ordered, the rationals are linearly ordered. So suppose that you have a linearly ordered set with no ends, meaning that there is no greatest value and there is no smallest value. And then it's countable, meaning that there are countably many elements. You can make a bijection with the natural number. And it's dense, meaning that between every two sets, there is another one, right? And between those two sets, there is another one. And between those two elements, there is another one. Between those two elements, again, there is another one, and so on, right? And so every order that has this property is linear with no end, it's countable, and it's dense. It's isomorphic to the rational, meaning that you can make a bijection with the rational such that if something is before another one in one order, is also going to be before the other one in the other order, right? And this is nice. It means when we have countably many points, linearly ordered, dense, those are the rational. So that's the first thing that Cantor proved. The other thing is the idea of a completion of a linear order. And the completion here is a little bit complicated. It has to basically be with supremum and infimum. If you get a set, you can always find a smallest greatest value, or a greatest smallest, a greatest smaller value, right? You can basically bound it with two elements of the set. So for example, the rationals are not complete, because if you take the set of all the elements that are less than pi, right, there is no greatest element there is no smallest element that is greater than all of them, because you're missing pi. You're going to have lots of things that are greater than pi, but there is not going to be a smallest one. And so the rational, the reals are the completion of the rational, meaning that they fill all these gaps, so that you always have the supremum and the infinite and the infimum. And basically, it's a theorem in order theory that every completion of that every order can be completed, and every completion is unique. Therefore, the real is the completion of the rational. So now this means that every complete linearly ordered set with no ends that has a countable dense subset, which would be the rational, is ordered homomorphic to the real, because this set is the completion of the rational. So whenever you have something that is ordered, and you can find countably many points in that order that are dense, and the order that before was complete, then you get the rational. So that's basically one of these results that, again, are in the foundation of mathematics that we need to actually justify and do the things that we need. And so now we need to essentially make an argument, and we're not going to have time to go through the full argument. At least we want to give you an idea of what are the things that we need to put at the beginning, such that we can recover the reals as being disordered. So how do we order things experimentally? How do we define order and quantity? Well, we have a way to compare two things and say that one is bigger and smaller than the other. Note that exactly the same is a little bit more difficult. If you have a scale and you put something that is heavier than the other, you will see the scale tip. But the scale might remain the same even if the two weights are not exactly the same, right? So it's a lot easier to say that things are before and after, where the things are exactly the same is a lot more difficult. So we're going to define a reference, which is going to be a tick of a ruler, a notch of the clock, or a sample weight on a scale. There is something that allows us to distinguish between a before and an after, right? And these references are fat, that are not infinitesimal. So you could be before, you could be after, or you could be on, or you could have something that it's a little bit before and a little bit on, a little bit on and a little bit after, or before, on, and after. And we want that after and before to be verifiable statements, because those are the things that we can actually consistently verify. We can make a cutoff and say, yeah, we're definitely above, or we're actually below that reference. And so we are going to define this mathematically. We're going to define the reference as a collection of three statements, and a before, an on, and an after. The before and an after are verifiable. An object can be on the reference. We need to have the reference. So there has to be an on. There can't be no on. We can't just have the before and after. We need the on. If it's not before and it's not after, then it has to be on. So the case where we are, if we're not here, we have to be here. And if it's before and if it's after, then it also has to be on, right? That is, and so we don't have all possible assignments for this table, right? The assignment false, false, false is not going to be, it's not going to happen. And also true, false, true, it's not going to happen, right? So these are the basic requirements that we can have on statements, on references. The first thing that you need to be able to get to a linear order is that you need to remove the overlap. Otherwise, you're not going to get to a linear order. It becomes a lot more messy stuff. So you need to be able to say that the thing that you are measuring, it's always either completely before, completely after, or completely on, which basically means that the extent of the thing that you're measuring, right, it's very small compared to the size of the on, right? So your tick of the event that you're doing, it happens faster than the resolution of your problem, for example, something like that. That's not enough to have a linear order, because you could have two references that are not aligned. Like, for example, if you have this, if you are in space and this is a before the reference and after the reference, we have two references like this, we could have all the 9 combinations, and this would not make the things, the references align, and then it's not going to give you a linear order. So we have a definition of a line that has to be general enough, and it turns out is the way that you define the alignment is that you look at the before and the after, and the not after, sorry, the before of both references and the not after of the two references. So you say that these are aligned because if it's before the first one, then it has to be before the second one. And if it's before the second one, it's not after the first one. And if it's not after the first one, it's not after the second one. So you basically have this chain of implication between the references. And the insight is that this ordering, that this is going to be an ordering of, in the logical sense, it's an order in the implication, and implication actually creates a partial order. This order in the logic structure will become the order in the points, such that 1 is before 2, precisely because if we say that something is before 1, it's also going to be before 2. So this implication in the statements is what then is going to give us the structure of the ordering of the points, which I find absolutely beautiful and interesting. Now, that's not, again, not going to be enough to get to the linear ordering, because you might have overlap within the reference, and you need to be able to resolve those overlaps. And there are 2 types of overlaps that you can have that you need to be able to resolve. The first, an actual overlap where you need to basically distinguish whether you are on this part or on this part of the reference. And then the sort of the overlap of the open parts. You always need to be able to put something in between if there can be something in between. And this basically gives you a refinable reference system. You can always go and figure out if there is some empty space between 2 references, I can always put something. And if there is some overlap between 2 references, I can always also put there something to distinguish this. And with lots of pages of proofs, you can then show that to define an order sequence of distinguishable cases, so of this instance of places in space, in values for some different quantity, then these are necessarily a sufficient condition. The set of references have to be strict, they have to be aligned so that you get a shared notion of before and after, and they have to be refinable such that the overlaps can always be referred. And this gives you points with an order topology. This is the hard bit to get. Once you have that, knowing whether you have real numbers or integers is just whether you have a dense set of references. Where you have 2 references, you can always put something in between. If you can always put something in between, you have the integers. And if you can't put something in between, then, sorry, if you can always put something in between, you can have the real numbers. If you cannot put something in between, you can only put infinitely many, then you're going to get an integer. And Now, what happens is now that we have clarified these conditions, you can say, okay, are these things that are tenable, for example, for something like space and time? Like, can we really say that these are things that we can keep, or they are idealization? And of course, so they're going to be idealization. And so, for example, the fact that the references are strict, as I said, it means that the resolution of the reference system is a coarse comparing to the width of the elements that we are actually looking at. And so if the tick of the clock have an extent and the events have an extent, and these the extent of the events and the tick of the clock are comparable, right? Because at the end of the day, we are going to use events to create clocks. Then you can't say that the references are strict. So it has to fail if you can't make that approximation. Now, another problem is that clocks have jitter. So they do this. If references keep doing this, then the references are not aligned, because sometimes something is going to be before, sometimes it's going to be after. So you're not going to be able to say that every time that this is before this reference is going to be before the other reference. So the lack of perfect synchronization means that your references on repeated experiments and so on, they're not going to be aligned. You can't guarantee this logical structure. And then the other problem, of course, that you cannot make ticks as narrow as you want. And so that means that your references are not going to refinable, because at some point you're going to have a finite, not a finite width, but a minimum width that you can't resolve anymore, but you're still going to have overlap between these references. So you're not going to be able to resolve this overlap. And so the problem with this is that you're not going to be able to have a consistent notion of before and after. So remember, these three conditions are there to give you an ordering, not to give you the reals. So what happens is that if you have to give up those assumptions, it's not that you give up the reals, but you get the rationals or you get the integers. You have to give up the notion of ordering. So the failure that you should have, it seems that has to be a lot more catastrophic. So the way that sort of it fails, I don't know how we resolve it, of course, I just know how it fails, but this is the structure that you can imagine, right? You can say that this is before this, and that this is before this, and that this is before this, but you're not going to be able to say that this is actually before this, or that this is before this. Like you can imagine to take this and swap it with this, and I can swap it here, and the ordering will still be preserved, right? So you're not going to have this a linear order that it's going to save you and give you like some nice quality. And one of the things that it's interesting to me is that you basically, what we would want, it's something that does not have order at small scale, but it has order at large enough scale. So I'm not going to be able to say whether two events that are very close to each other are one before the other. But if they are very far from each other, I should be able to say, yeah, this one is before the other. And in the current mathematical tool have a hard division between topology and geometry. And which means that the way that you distinguish things, and because experimental verifiability means distinguishing things experimentally, it does not depend on the size, right? It's a separate thing. And here we're saying that it's exactly the opposite. The way that we can distinguish things has to depend on whether two things are far apart or close behind. So there has to be a link between the topology and the geometry. You're not going to be able to define the topology without knowing the geometry, and vice versa. And so if this is the case, and again, these seems to be very simple reasons that are sort of very simply grounded, then it would mean that we most likely would need new math. When again, I have no idea what this math would be, and right now I'm not working on this. But if, again, this is something that we were discussing yesterday, I do think if somebody wants to seriously look at what are the mathematical structure that you need to look at this problem closely, and they're very hard problems, because I don't think there is math that you can simply go look and, oh yeah, you're going to find the problem solved. So That's basically it. So the main takeaway is that the real numbers can be recovered from essentially an idealized metrological model where you have references and you can establish before and after with these references. And the ordering of value comes essentially from the ordering that you already have in the logical structure given by this narrowness operation that you can think as implication. So 3 is less than 5 precisely because there are less than 3 items implies or is a narrower statement than there are less than 5 items. The harder part is the ordering, not the continuity. And the difference between the real and the integer, it's basically trivial. It's just the ability to find something always in between two references. And the interesting part is, if you remember that the Cantor requirement for ordering of the reals, that it has to be complete. And what's happening here is that it's the topology that is forcing this ordering to be complete by the way that it's being constructed. And the outcome of having found these set of assumptions for getting the reals is that the failure of idealization under the real numbers actually would lead to a structure much richer, much more complication than a real order. And again, it, to me, is a completely open problem of how that would be described. So again, this is why I think that finding, we were talking about before, what happens is the axioms that you have are not large enough. Doing these things, it actually make you bubble up all the problems that and all of the assumptions that you have to take to do things, and therefore you're much better in position to understand whether the axioms that you have can actually be general or not. Okay, so now let's go back and talk about ensembles and ensemble spaces. We saw before that we were trying to characterize ensembles and mixture of ensembles. That's part of a bigger project to basically define states and processes. And for states and processes, we need an in. We need something else that tells us how do we characterize this. And what we found, essentially guided by the work on reverse physics, we found that ensembles are really the key. But then, of course, you have to physically justify why do you need ensembles. And so we have this principle of scientific reproducibility that tells us the scientific laws describe relationship that can always be experimentally reproduced. And the fact that you have to be able to reproduce them right now is not just a matter of just having one verifiable statement verified once sometimes. No, it's the fact that you have to create it experimentally over and over. And what this means is that the laws cannot be about specific measurements at specific time. They have to be about collection of preparations and collection of measurements. And therefore, the scientific laws are really relationship between ensembles. So when we write F equals MA, we're not just saying, I have these numbers. It says whenever I prepare F in particular ways, I'm going to have an A that is prepared in particular ways. And so the physical theory, any physical theory, must at least describe which ensembles are possible within the theory, because I'm going to have a preparation procedure, which is going to give you an initial ensemble. I'm going to have a physical process, which is going to give me a final ensemble. I'm going to have a measurement procedure that is going to give me statistical data, and statistical data is an ensemble of the possible outputs of the measurement procedure. So at the very least, a physical theory needs to give me an ensemble, and therefore we need to find what are the basic axioms, something that all spaces of ensembles need to guarantee. And just to have some concrete idea of an ensemble, if we have a classical discrete space, we are going to have a series of points and a probability distribution over the points. If we have a classical continuous system, we have a phase space, we have a symplectic manifold, and then we have the space of probability distributions over that manifold. And if you're in quantum space, you have a projective Hilbert space for the set of states. Then your ensembles are these density matrices, the positive semi-definite information with trace one. So these are basically our target things. And whenever we make an axiom on ensemble spaces, we want to be able to make sure that these are going to satisfy, and we want to be able to recover these cases in the specific for the different things. So the first axiom of that we have is the axiom of ensembles that tells us the state of a sigma of a system is represented by an ensemble, which represents all possible preparation of equivalent systems prepared according to the same procedure. And the set of all possible ensembles for a particular system is an ensemble space. So we know what an ensemble space, and since it has to be verifiable experimentally, definable experimentally, we know that it's going to be a T0 second countable topological space. And what is going to be key for us is the topology is what is responsible for handling limits and infinite operations, and all the other operations that we have in the space are finite. And this is similar to what happens, for example, in topological vector spaces. The vector space has a finite structure, but the topology tells you how you get limits and out. We have what we said before, that if we have two elements A and B, if two ensembles A and B, we can make a mixture, and this P bar, it's this 1 minus P. So we have PA plus P1 minus PB, it's a convex combination. And geometrically, you can always represent the convex combination between 2 points as a point that lives on the segment in between them. A linear combination of 2 points, if I have 2 vectors, if I had an origin here, right, that would be the vector A and that would be the vector B, would span the whole space. But if you have 2 points and in a convex space or in a vector space, the convex mixture, the statistical mixture is going to give you a point in between. And again, only the finite mixtures are guaranteed, because once you know how to make 2, you can make n mixtures. But the topology tells us where do you have where will your limits converge. And again, we are trying to develop this theory as similar as possible as topological vector space, because topological vector space is well developed, and it's what one uses to generalize analysis and do all of those things. But there is no theory of topological convex space. And this is what we need to build. So this is exactly one example, like an exact example in which we don't have a mathematical structure that fits nicely, that is the mathematical structure that we would need if we started from physically meaningful starting point. So, and we're slowly building it. And of course, if we can engage some mathematicians to help us, would be even better. Then the third thing that we need to define for in an ensemble space is an entropy. And the entropy here is not some abstract quantity, it's something that quantifies the variability of the preparation of the ensembles. So if we have a set, and this is an ensemble, the ensemble is going to be all these infinite collection of preparation. There are going to be a bunch of things. And B is another preparation, is going to be a bunch of things. And you can see intuitively that this is less varied than this. And this is a statistical property that it's important because you're going to be able to see more variation in the outcomes here than here. So it's something that we need to be able to keep track. And the entropy, turns out, it's the thing that is going to tell us how similar are the preparation within the ensemble. Now, as you see, this right now is just defined as a function that is that takes an element of the ensemble space and gives us a number, and then it's going to satisfy a bunch of property. The first one is going to be continuity, because again, the entropy of an ensemble is something that we can go out and measure, and therefore it has a physical consequence. So therefore it has to be an experimental relationship, and therefore it has to preserve the topology. So it has to be a continuous function. It needs to be strictly concave, meaning that if we have two ensembles, right, and we put them together, right, so we have ensemble A and ensemble B, and we put them together, the output, the variability after the mixture cannot be less than the average variability of what we put in. So if we have the things that have certain variability and we do a mixture, we can't have now something that is better precise. It can only be something where the variability increases. And if it stays the same, then it means that we're actually mixing the same thing. And this is what justifies the strict concavity. Strict concavity increases, the average entropy increases through mixture, and the quality holds only if the two elements are the same. And so this is a very simple thing that we can justify by knowing that the entropy is is describing the variability of the ensembles. Another thing that we can justify is that there is going to be an upper variability bound. So suppose that the maximum increase in variability is going to be when we're mixing two things that are completely different from each other, right? That no element of A, no instance of A could be thought as coming from an instance of B. So these are two completely different things, such that when we mix them, we're only going to mix things that are completely different from each other. And that's the case where the ensemble are going to give us the greatest possible increase in entropy. And at that point, the increase in entropy is fully determined by the mixing coefficient. If we're mixing coefficient 0, we're basically not doing anything. But if we have a mixing coefficient 1/2, we expect the things to be much greater. And so this is going to be the fact that we have an upper variability bound. We have the entropy of the final mixture, we have the average entropy of the initial, and then there's going to be an increase that is given by P. And if A and B satisfy this upper variability bound, then we define these things to be non-overlapping. Like it's the fact that they saturate the upper variability bound that tell us that they are maximally different. Or we also call them orthogonal because the notion of orthogonality that we have both in classical mechanics and quantum mechanics in all the vector spaces that we really need is actually this notion. It comes out of the entropy. And so this is, again, something that can be fully justified by the fact that we know that there is a variability. And then the other thing that we have as an axiom is that if A is orthogonal to B, means that all the elements are different, and A is also orthogonal to C, meaning that, again, they don't have any elements that are similar, then A is also orthogonal for any mixture of B and C, because if the elements are different, they're going to be like, you can't create different elements when we're taking mixtures. And again, this makes the space what you would expect, where the orthogonality have these types of properties. Okay, so basically we have here now that the ensemble variability is what give us the entropy. And again, there is no standard theory of this type of entropic space that we're trying to define. And so this is part of let's say, of researching math, right? We need to find the theorems, what are the things that these axioms are going to give us, how much they're going to give us. Are they going to give us all the things that we need or just partial things? For now, we know that we can actually justify these axioms and we can go. I'm not even 100% sure whether all these axioms are independent. I think that part of this axiom is actually already inside the previous axiom. Maybe this axiom could be proven to be redundant. I don't know. That's part of the sort of the thing that people do in the foundation of math. When you have different axioms, figure out which one are independent, which one are equivalent. Now, we need to be able to do these type of things, right? And again, I'd be very happy to do this with other people, partly because it's more fun doing it with other people, but because they're gonna have different intuition and that. So the point is that these are necessary. Like we can say, okay, if we have an ensemble space now for any physical theory, even the ones that we haven't discovered yet, we know that at least we must be able to satisfy these axioms. And now the game is what it is that we can prove from these. And there are a lot of things that we already proved. Keep in mind that none of this is published in a paper yet. They're just results that they're putting in our book. Simply because it touches so many things that have no established field that it's even unclear to me where would we publish. And I'd rather to sort of finish the full theory first so that we know where all the pieces are. And then we can choose what are the right names for things and how the theory puts together and so on. Otherwise, you basically would try to write a paper that then after 6 months, you basically are going to say, oh, I should have done it in a completely different way. So we're allowing us that space, but the results that I'm presenting here are basically results that they're solved. So the first thing that you can do is that you can, this upper bound that we have on the entropy, you can actually derive that it's the Shannon entropy. So I have here a visual way of how the calculation, this is basically just a calculation. And again, you're doing this calculation in a general space, but this is basically how it works. The whole premise is that when you have a mixture of mixtures, you can do a full mixture first or break the mixtures into two steps. So if you have a uniform mixtures of n times m elements, then you can make it as a mixture of n elements of a uniform mixture of n elements, where the n elements are the uniform mixtures on the m elements. And so by breaking, by doing the full mixture first or dividing into two pieces, you're going to see that this part here has to be equal to this part here. And now you are going to see that this quantity depends only on n and m, and this only depends on n, and this only depends on m. And you have a sum here, and this is the entropy over the uniform distribution. So you're going to be able to say that the increasive entropy of a uniform distribution over n times m element is the sum of the entropy increase of an distribution of n elements of n elements. And so you have that the product becomes the sum, and that's exactly the property that the logarithm gives you, and that's what you're going to be able to say, that the increase of entropy over a uniform distribution is going to be some constant times the log of the elements over which we are doing the uniform distribution. Then you can say, okay, now I know how to do a uniform distribution. Suppose that I have a rational distributions, so that I have 2 15s, 5 15s, 3 15s, and 6 15s, right? Well, I can either do the mixtures over these rational elements. This shouldn't say uniform mixture. You should say rational elements. But anyway, you can again do first the mixture over. I know this is the uniform mixture. Oh, sorry, of all the things that decombine, of all the single elements, and then you can group these so that you obtain the rational distribution. And so again, you're going to have an increase of entropy if you do this mixture all at once, or if you do it into two steps. And that's what's going to give you this condition. And then you can take these conditions and get basically find the minus k p log p. That's basically how it works. And again, it's in the draft of our book. You can go and see the details, which unfortunately we don't have time. It's very nice. But the point is that the proof does not know whether we're dealing with classical ensembles, quantum ensembles, ensembles of any theory yet discovered. Like, it works in general. And the proof is basically short. It's about 2 pages of this type of calculations. And yeah, so we didn't need to put in the the formula for the entropy is actually derived from the previous axiom, which I find very satisfying. But everything that you can define with this notion of entropy, we saw before that we could define the orthogonality. So 2 elements are orthogonal if they saturate the upper bound, if they maximally increase the entropy after a mixture. But on the convex structure, we can also define 2 elements to be separate, meaning that there is no common component. So you can't find a C such that A can be seen as a convex combination of C with something else, and B also a convex combination with B and something else, right? So in the classical case, for example, this means that they have disjoint support, because if I have an overlap, then you can find a probability distribution within the overlap that then you can sum with something else to get one and something else with the other. Now, it turns out that in general, with the axiom that we have, orthogonality implies separateness. So if 2 things are maximally increase the entropy, then they can't have a distribution secretly that it's inside both of them. But the inverse is not true. The inverse is true, the converse is true, if you are in a classical space. In a classical space, if 2 things are separate, they are also orthogonal. But it is not true in quantum mechanics. For example, all pure states are going to be separate because they don't have components. The only component that a pure ensemble has is itself. It's not made of other things, right? And so all the ensembles, all the pure states that you can have in a block ball, they're all separate from each other. but only orthogonal pure states are orthogonal to each other. So it is not true that if you're separate, you're orthogonal. And the point should be that since this is essentially this is a defining characteristic, a defining line between classical states, classical ensemble space, and everything else, it should be possible to derive all other quantum-like features from this difference. I don't know how to do it, but that's what the math tells you. And that's very interesting because this is a completely different way of looking at these spaces, but it's of classical mechanics and quantum mechanics, but you are now comparing them, through some set of axioms that now are the same for both of them, which makes this comparison a lot easier to do because now you're talking about things that are similar to each other. Okay, there will be lots of other things, but we have to move on. Vector space constraints from the entropy. So it seems that the existence of the entropy makes the convex space a lot special. So first of all, convex spaces do not in general have a unique inverse, only if they are cancellative. But the entropy bound force this mixing to be invertible, which is very interesting because it essentially rules out a lot of cases. And this is one of those cases where I thought that non-cancellative convex spaces, I got excited, oh, maybe there is new physics there. And then I realized, no, actually, there is no physics. And then you can go through the examples and convince yourself that yes, that there has to be the truth. So this is where the math also guides, the physics and the math combined guides your intuition. Another thing that then you can prove because the space is cancellative is that ensemble spaces have to embed into a vector space. It's going to be a convex subset of a vector space, and the vector space can span further. So you're going to introduce unphysical objects, but it's, again, a convenient space to work with. And the vectors are basically differences. So if you fix A as your origin, then the difference between A and B is going to become a vector. And you're going to have a point on the other side such that if you mix C and B with an equal amount, you're going to get A. Then it means that the vectors between C and A is going to be the difference from, is going to be the negation of the vector between B and A. So basically, you can define all these vector operations defined from mixing operations so that you, again, you can keep tight the connection between these two things. And again, this is one, since we had the question about category theory before, some of these results I actually got from somebody that was looking at the convex spaces by themselves and had this theorem that proved that if the convex spaces were cancellative, they embed in a vector space. The construction that he had to create the vector space was very essentially, let's say, abstract algebraic categorically, in the sense that you basically take that, you make some closure, and then you quotient out with something. And the problem with those constructions is that even talking to other mathematicians, you can't build an intuition of what those things are. And since in our cases, we have to understand the interaction with the topology of those things, we couldn't get a good enough intuition. So this is one of, again, the problem of having math that becomes very abstract and you can't make concrete ideas. And in this case, we are looking at sort of a concrete version of convex spaces because it has more structure. And so we need to sort of analyze more what these constructions are so that we can get a better understanding. So anyway, we're going to have vector spaces, which is important. And another thing that you can show is that, as I said, the ensemble space has to be a convex set of the vector space, and this is our ensemble space inside the vector space. But not only is convex, it has to be bounded in all directions. And the way that you can prove it, and again, I got this intuition that this would be the case only by playing around on the Desmos calculator online and fixing things. And so let's say that we have 3 points, this point, this point, and this point. These are the ensembles over a line. So this would be the ensembles over here. And on the vertical side, we have the entropy. So we can fix 3 points at 3 different positions with some entropy. And then we want to have a 4th point with some entropy. And since the entropy is strictly concave, then this point has to be below this blue line. And since you have a bound, an upper bound, then this point has to be above this purple line. And so then you see that the two lines intersect, and therefore you can't put a point past a certain point. So this is the geometrical intuition. And then once I figured out how to do this, then I wrote the math, and the math actually checks out. So again, multiple ways of looking at the problem always helps. So these are some properties that we can get in terms of vector spaces. What we also can find is, as we saw before, there was a connection between entropy and geometric structure. You can also find this in the entropy in these ensemble spaces. You can define a sort of something that looks like a distance. If you have two ensembles, you can say how much does the entropy increase if I mix those two ensembles by 50% each. If they're the same, right, the entropy does not increase, so that is zero. So, and it's zero only if you're mixing the same thing. So you have a lower bound on zero that is only there if the two things are the same. And if it's maximum when they are orthogonal, and if we're measuring things in bit, then this is going to be 1. So this is a quantity that is going to be between 0 and 1. And it's also symmetric. And so it kind of is like a distance. It tells you how far two states are apart, except that it does not satisfy the triangle inequality. And this is actually something that recovers what is called as the Jensen-Shannon divergence, which is something that is defined in information theory. And if you don't know what this is, you might have heard of the KL divergence. This is a symmetrization of the KL divergence. But the point is that this quantity that is abstract, defined abstractly on the ensemble space, reduces to both the Jensen-Shannon divergence in both classical mechanics and quantum mechanics. When you have that, you can now define a notion of distance on infinitesimal change, on variation. And then what you find is that the strict concatenative means that the Hessian of the entropy is negative defined. So if you put a minus sign, which is what you find when you make this calculation, you find that you have a metric tensor-like thing on the space of ensembles, which actually recover the Fisher-Rao information metric for both classical mechanics and quantum mechanics. So again, with very simple calculation, the calculation is sort of trivial, but we don't have time to go through it. But it's something that fits in a page, and again, it's completely general. It doesn't care what the underlying space is, and it tells you that this thing always exists for any ensemble space. So again, if you want to create a new theory of quantum gravity, whatever, this is going to be there in some shape or form. And everything that we want to recover, not just geometric structure, but also measure theoretic structure, your probability measure, your count of states. So those are everything that we want to get. So in classical mechanics, you have the connection between the entropy uniform distribution and the logarithm of the count of states. And so can we do something like that for ensemble spaces in general? And it turns out that you can. Because the exponential of the entropy, right now we're going to start with the entropy and not with the count of states, right? So we're going to have to do the exponential of the entropy, which we also saw yesterday. It seems to be a quantity that recurs. The exponential of the entropy has a very nice property that it's subadditive. If you have two ensembles and you mix them, then the exponential of the entropy of the mixture is less or equal to the sum. And it's the sum only if you're combining ensembles that are orthogonal, which, for example, in the classical case would mean disjoint support. In the quantum case would be orthogonal subspaces. And if you're mixing them in the correct proportion, so that you're giving a higher weight to the one that is bigger in some sense. And so again, these properties are things that you can prove in general. Simple calculation on any type of space, which means so these are truly general things. And then what you can then do is define what we call a state capacity, and we call it state capacity because capacity is another name for a non-additive measure. So given a set of ensembles, we want to say how much is the spread of those ensembles in terms of the pure states that you could put in on the physically defined cases. So you take that subset of the ensembles, you take the space of all the possible mixtures, you get the highest entropy, because the ensemble with the highest entropy is going to be the uniform distribution. So you're basically saying, I have a subspace, I take the element with the highest entropy with the uniform distribution, and then I take the exponential of it. And then once I take the exponential of it, I call that the count of states. And in classical mechanics, it recovers the usual count of states, it recovers the Liouville measure. And if you're using subspaces in quantum mechanics, then it recovers the dimensionality of the space, which is the count of distinguishable space. So again, this is something that we can define very simply in general and recovers things that are interesting. And the only quirk is that this is a non-additive measure, meaning that if you have two sets that are disjoint and you do the measure on the union of both, you not necessarily get the sum of them, you're going to get something that is actually lower, it's going to be subadditive. Similarly, we have a notion of probability that does not talk about outcomes of measurement, but it's defined in terms of how do we mix things. So this is the thing that it's different in classical mechanics and any other space. And in classical mechanics, you can mixing things, so creating an ensemble or taking probability of outcomes is the same thing. So these coefficients that you use in the mixture are the same coefficient that you use when you get out a probability out of it. In quantum mechanics and any other space, it's not necessarily the case, and this is what is different. And so since we can't get a notion of probability that works both in classical mechanics and quantum mechanics on the probability of outcomes, what if we have a similar notion of mixture in classical mechanics and quantum mechanics such that it becomes the same? And it turns out that you can do, given a set of ensemble, you can ask, what is the biggest P that I can put in front of a convex combination of those such that I get my E? So if you have an ensemble, how much of this ensemble can I think as made of mixtures of all these other preparations? And you can define this. It's going to give you, again, another measure, but it's not going to be an additive measure. It's not going to be a subadditive measure, but again, it's something that you can define and study in general. So what is the point of all this? Well, we can, the argument here is that if we allow for the principle of scientific reproducibility, then that requires notion of ensembles, because we must be able to prepare repeatedly both preparations and measurements, and then the relationship of a physical law is going to be in terms of those ensembles. We can develop a theory of states and processes using ensembles, and we have right now a few physically justified starting points, but they still lead to a rich structure that recovers a bunch of things that we already have in classical mechanics and quantum mechanics, but we can do it over a general structure. And these notions, the thing that is mostly interesting to me, prepare a core foundation that can link various standard mathematical tools. What I mentioned yesterday, that one of the things that I realized while doing reverse physics is that all these different characterization use different mathematical tools, and you always have to translate one to the other. The idea is there should be a core physical theory that connects to all these different ways of looking at it, and I think that's what we are starting to see. Topological vector spaces are the foundation of modern functional analysis, and we can see that we do have a topology, and the convex space becomes a vector space. We need to understand how to get the, to see how we get the topological vector space. Information geometry can be shown to link to symplectic geometry of classical mechanics and the inner part of quantum mechanics. So it's very likely the geometrical structure that we're having, if projected in the right way on the space of idealized states, then we're going to be able to recover those structures. And non-additive measure provide a generalization of classical measures of theoretic structures. And again, maybe there is a generalization of the integration and differentiation that will make sense. And since there is a lot of work to needs to be done to the theory, but the point is that there are also a lot of nice results that once are found, they become very simple. So to wrap it up, physical mathematics, again, the goal is to derive the math from physical requirements. We have this notion of scientific objectivity with evidence-based assertions to get the notion of sigma algebra and topological and topologies, and real numbers can be understood as a modeling of idealized reference system. And we have ensembles from reproducibility. And again, so hopefully this gives you a sense that we can sort of do something that really goes in the nuts and bolts of the math while actually still keeping a sense of what these things are physically, and quite frankly, find also a lot of new and interesting math. So even for mathematicians, I think that this would be interesting. And that's it.
Let me see, Xinwei is still connected, and I had actually forgotten about a question they had asked previously during the other lecture. So currently it seems that there are way too many pieces of maths in the physics field to be made sense of.
What is the question?
Well, there's a question mark. So are there currently way too many pieces of math in physics to be made sense of within physics?
So let's put it like this. There is always an increasing number of math things because there are a lot of mathematicians that try to take things and create new things and so on. For example, just a couple of weeks ago, somebody contacted me because they're working on continuous logic. And they're working on a way to reframe quantum mechanics in terms of continuous logic, which I didn't know it existed, before he talked to me. There is a sense that a lot of the things that we need to do in physics are the things that we need to do in physics. So at some level, the mathematical structure that we need sort of in some ideal world are going to be those, and then those can be implemented in many different ways, right? So there are going to be multiple ways to define the mathematical structure that are going to be sort of equivalent to each other. So yes, there are people that do a lot of things, and not all of them are going to fit exactly the math that we need. My approach is to use come si dice, as much as we can the mathematical structure that are the most common. So, for example, I'd rather use a set theoretic structure than a categorical structure because the majority of the mathematicians that I'll talk to are going to be a lot more comfortable with those things. So even though the same structure can be described in a set theoretical way or in a categorical way, I'll go with the one that increases the chance that I get the collaborators. In the same way, when I recover topologies, I want to recover topologies with terminology that everybody in math knows and uses. Because the biggest problem is, again, creating a community that helps me analyze the thing in all that. And then, as always happen in academia, there is going to be too many things so that you can to be able to be aware of what everybody's doing. But fortunately, you don't need to be aware of everything that is there to be able to make progress.
Okay, Xinwei has clarified in the chat that was supposed to be a comment on the Clifford algebra question asked previously.
Right, so Clifford algebra, I looked at specifically because there were some results and I thought, oh, this might be nice. And so I sort of at least got a sense of what they are and how they work. But then I decided with the limited time that I spent looking at Clifford algebra, that I would be better off working with topological differential topology and sort of variational calculus, because those structures are going to be closer to the things that we need, right? And so those are the type of valuation that we basically do, and of course they're not always going to be correct, and sometimes you say, oh, actually, I should have used that, but.
A question from the chat from Shad Azmi. An integer-based reference system solves Zeno's problem.
So Zeno's problem is already solved by essentially, I can say, by calculus, in the sense that that's basically just a problem of making the limit. So what Zeno is doing is sort of like he's dividing things, but it's not making ratio of things. So it's dividing, let's say, the space, but not also dividing the time, and therefore that's how he gets the paradoxes.
Going to the Q&A, a question from Daryl. Can you elaborate on how completeness is implied by the topology? I remember completeness is not a topological property.
Correct. But if you have something that looks like an ordered topology, and so there are two things. So imagine that we have these references, right? And I can define these before and after. And now imagine that we have the references that are, all the references, let's say, that are, that tell you, how can I say? Okay. Let's do two things. The union of open sets is an open set. So if I take something is before, let's see, I have to make this correct. Something is before 3. Something is before 3.1. Something is before 3.14, and so on. Like I make the union of all of that. I'm going to have something is before pi. So in that sense, the topology allows essentially to make these sets, right, of something, let's say, is before a rational. Then what happens, if you remember, we had defined references such that I have a before, I have an after, but I always need to be able to put something in between, right? So a reference cannot have just a before and just an after with nothing in between. So if your order would not be complete, right, say that I'm getting the rational, I would be able to have something that I basically can be able to test the value is before pi. I'd be able to test that the value is after pi, but I wouldn't have that on pi. So I wouldn't be able to construct a reference. So with the fact that I'm describing references, the fact that I can make these unions, when I have a bunch of references, I can construct other references. And when I construct other references, I'm always going to be able to put something between the before and after. That's something that is the before and after. It's the supremum for the things before, and it's the infimum for the things after. And that's how it makes magically ordering complete. So it's not just the topology, it's topology combined with all these notion of references.
A question from Tobias. Regarding the axiom of entropy, it's plausible that we always have a notion of variability, but that we measure it with a real number, etc., is less intuitive. Is there justification in simpler terms? It looks like what we need is to distinguish elements and quantify their frequency in the ensemble or something like that.
So that's something that while writing the justification, I realized that I do not have a strong justification as to why the entropy has to be a real valued quantity. Assuming the entropy, the fact that you assume that the entropy is a real value quantity is because you're assuming that you can always take two ensembles and compare them by variability, and you are basically going to have a linear order between these equivalence classes of variability. So something is either more variable or less variable or equally variable. It can't, you cannot, you can always make the comparison. So if you have two ensembles, they have a variability, you can always say whether, you can always compare the variability. Either one is more variable than the other, or the opposite, or they're the same. And I currently do not have a justification for why that would be the case. I do think that it should still be the case, because I doubt you'd be able to define, let's say, deterministic processes between two things, because deterministic and reversible processes are going to be stuff defined at equal entropy. Like there are all these notions that come out from maps, right? If I have maps from one ensemble to an ensemble and process from one ensemble to the ensembles, if there is no order, like if you can't compare the variability, I think there are going to be a lot of other things that you can't define, and that would not make sense. I do not have all of these intuition nailed down in a nice justification. So right now, the justification says that there is this hole, and that we are basically assuming it. And that's exactly the nice role of the justification, because they allow you to notice that you were making this assumption, and then you can decide whether it's you still want to keep it or not.
Related comment from Luther in the chat. Entropy is a signed measure on R, so R is a very natural place for it.
Okay.
Currently, no more questions in the Q&A or the chat, but maybe I can raise something. So for variability of, people have talked about applying information theoretic ideas to pieces of writing. You can look at variability in terms of, say, letters or words. People have done this for Shakespeare, for example. So for physical systems, is it or how is it defined what the elements are that you're examining the variability of?
So this is where we are doing the opposite. We define the ensembles, and then the elements are going to be defined based on the ensemble and the variability. So the basic idea should be that even when we define, this variability could even be how much let's say, a macro state is jiggling around with, or the state is jiggling around within a delta t, which is the time scale that they're using to define that state. And so I cannot talk, so it's a little bit like the tests. The elements that are of the variability are the single instances of the experimental of the output of the experimental procedure, and the physical theory only knows and talk about the collection of those, because it's on those that you're making the statements. You are going to be able to define sort of the elements upon which you can define ensembles in the standard way, only if you're able to prepare those instances consistently and make an ensemble out of them. So I can talk about, I don't know, having an ensemble of characterizing the ensembles based on the fraction of two different molecules, for example. precisely because I can create ensemble of the same molecules, and so I know, and I can always produce this molecule. I know what it is. I can always measure it in the same way, and so on, because basically you're making an ensemble that 100% you are preparing that molecule or the other molecule, and then you can think, okay, now my mixture is a mixture of these two ensembles where I always prepared one molecule or the other. In the case where you would not be able to do that, because all the things that you're producing are always things that jiggle around, and they don't always have all properties always well defined. That's where you're getting closer to the quantum pure state. Like, you have reduced the variability of some feature, and you're characterizing the state by those variables of things where you reduce variability, but you still have variability on other things. So I characterize my spin up and my spin down state, and that's all that I can characterize. And of course, there is still variability, because if I perform processes and measurement on other things, I see that there is variability because I don't always get the same thing, right? But then I characterize my pure state based only on some elements, even though even in that pure state, not everything is well specified. Does that make sense?
I think so. Right, the ensembles are abstractions, right?
Yeah, some
very purposefully abstractions, of course, for the purpose of generalized ensemble spaces.
Like this is another thing where, you know, we are mixing ensembles with real numbers, and again, those real numbers are also idealization, and it's okay to have this idealization because the ensemble is an infinite set. So when I'm thinking about an infinite set, of course, I'm going to use a real number because that's going to be a limit process anyway. So this is where it's basically the problem that we were talking about the last time. Can you even create a physical theory where you are not, where you don't have some idealization somewhere? And if we're saying that, so we're saying right now that states at least need to be able to be described through ensembles. If we're able to show that that's the only thing that we can do, and the ensemble is an idealization because there is no such thing as infinite collection of things, that's where you're going to be able to say, oh, okay, then of course these are only models, and is only going to be about this fiction of things that are sort of idealization of the things that we actually do.
Sure, you're always going to have some kind of idealization somewhere in the system, yeah, or somewhere in your framework.
Framework, yeah.
Yep. Let's see other questions.
So if there are no other questions on this particular topic, you can also ask a question about anything of the project, or we can just close it and call it a day. You guys decide. Oh, I didn't see the comment. Yes, it's the order topology that allows you to define the completeness more than just a concept of topology itself. Yeah.
Do you want to make any comment on how this entropy can connect eventually to thermodynamic entropy?
Oh, I'd rather do it tomorrow when we are gonna talk about
yeah, sure. It'll be in the part of the open problems that have some ideas already.
I'd say we just close if there are no questions.
That is fine on my side.
Okay, so I thank everybody for for sticking it out for this second day, and I'll see you guys tomorrow if you're here.
Thank you.
Bye. Okay, this time the stream